Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start with a miscellaneous topic of digital electronics. So we have covered everything for digital electronics. This was one topic that was left out which you guys were asking. So I have bought this lecture for you. So obviously you know the drill. Like the video if you are enjoying the concepts and don't skip this video because it is a 30-minute topic and it is very light topic. Don't take it too much deeply. You don't have to go too much in depth of the everything. Okay, just understand on the surface level. You just need to understand the theoretical topics because gate can ask theoretical questions from this and they have asked. Okay, I will tell you they have asked. We will solve few gate PYQs as well. Okay, so this is a 30-minute topic, so just study this lightly and that's enough. Okay, that's what you need to know. So we will discuss about semiconductor memories. Okay, so first of all we will understand why do we need semiconductor memories. What is the need of semiconductor memory? Semiconductor memory is a type of computer memory built using semiconductor based circuits. What are semiconductor based circuits? Mainly MOSFETs and BJT, right? Mainly it is MOSFETs only, and BJTs are sometimes also used. Mainly MOSFETs and BJTs. Okay, MOS and BJTs. It is widely used in modern computing systems to store both instruction and data. So, like you know, right? A program needs both instruction to store. It needs to store both instructions and data. If you have studied COA from me, you will know. Also, it would be better if you have already studied the COA and then study this. Just one concept I will tell regarding that concept, regarding which is linked with the COA. So it would be better if you have studied COA and then you come back here. Okay, that is my recommendation. So obviously we need to store data, like whatever this phone, right? You have your videos, you have your photos, you have your PDFs, assignments, all those things you need to store. That is data. And obviously you need to store the apps are what? Apps are programs, like your Netflix, like your Hotstar. Those are programs, right? But that also needs to be stored, right? That is just a written code that also needs to be stored. Obviously we have to store that as well. For that we will need memory is required, obviously. So there are mainly two types of memory. One is program memory, another one is data memory. Program memory stores the instructions that the computer executes. Data memory holds the holds data that the instructions operate on, like write to this register, read to this register. That is instruction that also need to be stored, right? That instruction also needs to be stored. Then write 1, write 0. That 1 and 0, that is the data that user is telling to write at the register, right? That is the data memory that you need to store. So these two things are required for memory. Okay, that is a need of memory. So one more thing is that in memories, right, I have like if you know few basic terminologies. First term is 1 bit storage. 1 bit means, what is a bit? Bit means 0 or 1. So whatever we store, right, whatever is we store in computer, and you have, I know you have already studied digital electronics, whatever we store, it is stored in bits. Okay, zeros and ones. So just that is what we'll do here as well. We'll store in zeros and ones. Okay, so 1 bit storage is a flip-flop. It is simply a flip-flop. 1 bit storage is simply a flip-flop that is stored using a single information, a single bit of that stores a single bit of information. You can consider this as D flip-flop. I will take an example as well, don't worry. But I hope you have studied digital electronics. So obviously first thing is you have to go back and study all the combinational circuits, sequential circuits and combination circuits, right? Then only you will be able to understand about flip-flops and all those things, right? So it will be better if you have revised your flip-flops topics. You will understand this. So basically 0 and 1 can be stored using D flip-flops. We modify that as well. We modify it as well to our betterment for storing data, right? We modify. I will show you that thing as well. Now, if a flip-flop is required to store a single bit of data, then how many flip-flops will be required to store n bits of data? For n bits of data, we require n flip-flops. Now, what we do, we have a new unit known as registers. What are registers? Registers are basically combination. Generally, it is nothing set. It is a combination of 8 flip-flops. Okay, it is a combination of 8 flip-flops. So 8 flip-flops together make a register, and one register means 8 bits. One register means 8 bits, and 8 bits are generally called as 1 byte. Okay, so this is nothing concrete. Okay, this is nothing concrete, just a notation. It can be, one register can contain 16 bits as well. It depends how they are making the registers. So basically we write one register is equal to, so one register, I will write here, one register one register is equals to 8 bits. That is the general case, but it may be different as well. It can be 16 as well. Okay, but one thing is for sure, that it will always be a power of 2. Okay, it will not be like it is not a power of 2. It will always be a power of 2. That is what you have to understand. Okay, and for obviously we don't store 8 bits, right? We store megabytes of data, we store gigabytes of data, we store terabytes of data. To store terabyte, gigabyte, we use large storage. Basically, for storing large amount of data, multiple registers are grouped together to form a memory. Obviously, if you group things together, right, it becomes easier to form the memory. Now we'll just discuss a bit about memory organization. Okay, you can like study from me about this memory organization, COA. Just watch the COA part 1 lecture. There I have explained all this, right? How we store the data, how it is organized. I will just explain one example, and from there I will discuss. I will not go too much in depth here because this topic has already been covered in COA memory, in COA part 1. Okay, COA part 1. So memory is organized in form of matrix of rows and columns. Each row represents a memory location, while each cell in this row stores 1 bit of data. Okay, so like each row, like it is formed in an array, right? It is memory is stored like an array of data. So each row stores a particular set of data. So this is one of the data together. This is one of the data together. Now what you cannot do is, this is one data 1010. Let's say I have only a 3-bit data. Let's say I have only a 3-bit data. 101. Okay, you can store this in this location 100. Okay, so how will I store this in this location 100? I will store it here. Let's say I will store it here 101. Okay, you might have a doubt, what if, sir, I stored it like this 101, then this space is empty, right? Let's say the next data I want to store, next 3-bit data is 110. You will say, sir, I will store this first bit here because I have already a space left here. I will store this here, and then I will store the other remaining bits here. You cannot do it. You cannot do it because few things are predefined in the in our processor, in our computers. Okay, this will be predefined by the manufacturer, that each row, right, will contain how much bit of data. If I have a single number a is equals to let's say I'm just writing a 3-bit number 7. Okay, then how will I store in 100 location? Because each location will store a single information. Okay, this a will be stored here. Okay, so this, right, I will convert it into 4 bits because I know I am converting in groups of 4 bits, so I will convert it into 4 bits. How will I convert it? This will be 0 1 1. Okay, then I will store this here because 0 at the front doesn't make any difference. So it doesn't matter if I keep 0 or not keep 0, it will not make any difference. So what I will do, I will keep this 0 1 1 1 here. Okay, so it won't make any difference. So this is the basic thing that you need to understand. This I have taught in my COA, so I am not going too much in depth here. Basic thing is, now this variable is stored here, and I know what is the location of this variable 100. So like you are at your home, right? You have address. Inside the address, they know what is the data. Basically, you are present, your father are present, your mother is present in your address, right? You live in Delhi. Okay, Delhi, this colony, JP Nagar. Okay, something like that. So this data also will have to have its address, right? This variable a will be stored somewhere. That somewhere is the address of this variable. Okay, in the memory. So memory also has a address. It needs to address, right? Because how will I locate a particular value? I need to locate a particular value. How will I locate that value? By knowing its address. So a has an address of 100. So in the 100, it will be stored like 011 011 in the bit format. Okay, I hope you understood this. This I have taught in my COA as well. Okay, just one thing that we need to understand is, how many address lines will I require to store n bit data? Okay, that you need to understand. Let's say generally they give in this format, a 8x4 memory can store 8 locations with 4 bits each. So what does 8x4 means? 8x4 means basically I have 8 locations. Okay, and 4, this last number, means each location can store 4 bit of data. That is the meaning of this term, 8x4 memory. Okay, so that much you have to understand. And what else you have to understand? That each memory location is uniquely identified. So each memory location will be obviously uniquely identified by the address. And now what you can know is if a system, now I am going into the system, okay, if a system has 8 address lines, so in a computer they will have 8 address lines. Basically their meaning, they have 8 address bits. This I have taught in COS, so I will just explain with the bits thing, this you will understand. If a particular architecture has 8 address bits, then how many unique address I will get? It will be 2 raised to power n, because obviously my range will be from, like if I am starting from 0, it will go from 0 to 2 raised to power n minus 1. This will be my range, and how many addresses are defined here? Total 2 raised to power n. It's very simple, okay? And then what will be the size of memory? So in this case, can you tell me what is the total size of memory? Size of memory is generally told in bytes. You can told in bits as well. Here, can you tell me what is the size of memory? Here, each location can store 4 bits of data. How many locations I have? Total 8 locations. So it is 8 into 4, which is written over here. 8 into 4. If I have 8 address lines, okay, 8 address bits, how many unique address locations I will have? The 0 to 2 raised to power n, that is 2 raised to power n. So I will have 2 raised to power n unique addresses into the data width per address. It depends, right? It depends. If I have, let's say, 8 bits per address, then I will write here 8. Okay, if I have 4 bits per address, then I will write here 4. So this will be data width. Now, if this data width is in bits or byte, generally we define our memory size in bytes. So if this you are writing in bits, then what you'll do is, what I know is 8 bits is equals to 1 byte, correct? So we'll divide this by 8. Why? Because I have to convert this back into bytes. Okay, this will be in bytes. Or I can write the same thing. You define your data width in bytes. You define your data width in bytes. Okay, doesn't matter. You define your data width in bytes. Okay. So whichever one is suitable to you, you do that. So this also will work. Then you don't have to divide by 8. Already the unit of bytes is taken care of. All this is defined in bytes. That is what you have to understand. So few important terminologies also, that 2 raised to power 10 is known as kilobytes. Why is it called kilobytes? Basically, what is 2 raised to power 10? 2 raised to power 10, right, is 2 raised to power 10 is 1024. So I can roughly write this as 10 cube. And what is 10 cube? 10 cube is simply kilo, right? 1 kilo. That's why we write it as kilobyte. Now what is 2 raised to power 20? 2 raised to power 20 will be roughly this right will roughly be equals to 10 raised to power 6. You will see it is roughly equals to 10 raised to power 6, which is defined as 1 mega, which you already know. And 2 raised to power 30 is roughly defined as 10 raised to power 9, which is known as giga. That's why we write it as 1 giga. And 2 raised to power 40 is defined as 1 raised to power 10 raised to power 12, which is roughly defined as 1 tera. So these are few terminologies that you should know. Okay, these are few basic things, theoretical things, aspects that you should know. Okay, now I will come to the semiconductor memories portion. This is the most important portion. Now you have to listen to me very, very carefully. So in semiconductor memories, right, we mainly have two types of memory. One is ROM, another one is RAM. Now what is the difference between them? That you will understand today exactly. So first of all, both, I will write here, both are random. Both can access the data randomly. I know this is a misconception, but both randomly. Okay, first clear this misconception that which can access the data randomly. Both can access the data randomly. What do I mean by randomly? I previously told you that memory, right, in memory data is stored in this format. In location 100 I will have some data, in location 110 I will have some data, right? Location 104 I will have some data. Random basically means if I tell the CPU give me the value of the location 104. It will directly go to this value and then fetch the value. What is the other one? Other one is sequential axis. Sequential axis actually depends on the location of the data. Why it depends on the location of data? If you remember CD, like I know new generation people won't remember this, but old generation guys, we know previously, right? We used to store data in CDs, okay, in magnetic tapes. So in CDs, what used to happen in hard disks as well, now latest generation hard disks, their access is random, but old hard disks, right, not SSDs, old hard disks, they are sequential. So in CDs, what used to happen is that we had this, I don't exactly remember the name of this particular handle. So this handle, right, used to touch the CD, okay, and the CD used to rotate. Now let's say if I want to access the memory location, let's say like I have address from 100 to 200. Let's say I want to access the memory location 180, and if I want to access the memory location 101, the access time of both these different types of memory locations, right, will be different. Why it will be different? Because here, if you observe one thing, that as this is rotating, if I am starting, let's say this, right, this is initially this was 100 location, and then it will slowly increase. This will be 101, this will be 101, this will be 102, and so on, right? This is a complete circle. So obviously I will get the value of 101 when this CD rotates, and this 101 comes here, right? It touches, and then I get the data. But to access 180 will be somewhere here. Okay, so it has to rotate this much amount of angle, then only I will be able to get the value of 180. So here the access time depends on the location of data. Okay, that's why we don't use it in RAM and ROM, because there we need we need the value of data instantly, because CPU is in direct contact with the RAM and ROM, so we need the value of data instantly. So that's why we don't use these type of sequential access in RAM and ROM. Okay, that is the difference between sequential access and random access. Random access, all memory locations can be accessed at the same amount of time. I told you, right? It doesn't matter if I access location 180. It doesn't matter if I access the location 101. I will access the data in same amount of time. In sequential, it may take me here 3 seconds, and here it may take me only 0.1 second. Okay, but in random, okay, both 101 and 180 both will take 0.1 and 0.1 second. Now you might say, why then we are using this? What is the point? Obviously it is cheaper. This is cheaper. Okay, and if it is cheaper, we can store large amount of data here. Okay, where we are not concerned with the speed, we are just concerned with storing the data. This is obviously expensive. Okay, that's why we don't use it everywhere. If you know a basic thing about computers, SSD, right? SSD and HDD, both things are same only. They are storage devices, but you will see SSD is very, very expensive than HDD, that is hard disks. Why is it so? Because you have higher speed, copy and paste, you can do very fast, but the problem is it is very expensive. Okay, to make those things, it is very expensive. I hope you understood this point about sequential and random access. Now I will come to the differences between RAM and ROM. Both are random access only. Okay, this point is written in the last point basically. Okay, now ROM is read only. We can only read the data from it. We cannot write it. There are few types of ROM in which we can write as well, but mainly we use it for read only purpose. This is mainly used in firmwares and all those things where the user is generally not programming it. So generally it is not programmable by user. This is the generally I'm talking about. Sometimes there are few types which ROM can also be programmed. Okay, I will discuss about those times at the end, towards the end of this lecture. Okay, another thing, ROM is non-volatile, RAM is volatile. What do you mean by volatility and non-volatility? So non-volatile basically means that here, right, here, non-volatile basically means that if I turn the power off, if I turn the CPU off, right, whatever is inside the ROM, whatever data is inside the ROM, it will be deleted. So power off, and everything lost. Okay, but for non-volatile, even if I turn the power off, the whatever data was there in the ROM, it will be present, it will be permanent, it will be permanent, it will not be lost. Okay, it will be permanent. Now, ROM generally it is system or manufacturer programmable. It doesn't, like, user does not do anything here. If you know a few things like BIOS, okay, in your CPU, in your computer, laptop, you have a thing named BIOS. Generally, we don't touch the BIOS until and unless we really need to. We can change few manufacturer things on the BIOS, right? We don't use it, so user doesn't touch it. But this is user programmable. RAM is user programmable. Basically, RAM basically stores what? It stores the tabs that you're using. This phone, right? In this phone, I'm turning on Netflix, I'm turning on Hotstar, then I'm turning on what do you say, Google Chrome or some other application, right? Those are stored in RAM. Then I can change those things, right? That's why it is user programmable. Generally, ROM is used in firmware or system level programs, and RAM is used in main memory and for use for temporary data storage. Okay, these are the use cases for RAM and ROM. So now we will discuss more about SRAM. Now you have to listen to me very very carefully. So in sorry, not SRAM, more about RAMs. Okay, RAM are mainly classified in two types. One is basically one is your static RAM, another one is your dynamic RAM. Okay, so static RAM stores data using flip flops. Static RAM stores data using flip flops. Uh, and your sorry, yeah, so I will explain this one by one, don't worry about this. So I'm just explaining what are these things. So it is more faster, okay, but has lower memory density. But dynamic RAM is slower but has higher memory density. Obviously you gain some, you lose some. Okay, and it stores data in capacitors. Like in dynamic RAM, we store the data in capacitors. So we'll understand this, don't worry. Which require periodic refreshing. Why do we require periodic refreshing also, that we will understand. It has it is used mainly in main memory, and it is used in cache memory. Why? This I have taught in COA, so this is not that important. In cache memory, right, we need very high speed. We need very high speed for cache memory, so that's why this is used. SRAMs are used in cache memory. In main memory, not that high speed is required, but still high speed is required. That's why we use DRAM to save the cost. Okay, so just one thing. In SRAM, your basic memory element, okay, your basic memory element is flip flop, and your DRAM, your basic memory element, is capacitor. Only these two things you have to understand. Okay, so now I will discuss about static RAM. What is static RAM? Now, if you have studied digital electronics, that's great. If you haven't, you have to revise the latches part. Okay, so this, right, these are basic memory element for static RAM. Now we will implement this with MOSFETs. Okay, mainly the basic building blocks are this only. We will implement this using MOSFETs, and that the name there is static RAM. That's it. Okay, here how, like, can you store the data? Yes, right. If I have a 1 here, okay, then this is 0, this is 1. So if I take the data from here, right, I can store the data. This also is a latch. This also is used for storing the data. Okay, if I have a 0 here, then I will have a 1. Okay, that's it. That's the basic thing. I can store either 0 or 1. How to store, right, I will explain, don't worry. How do we store the data, I will explain. This also is like, this is the same circuit diagram. This is nothing different, right? Just I've connected them in a flip-flop manner. And what is this? This, if you remember, is just like a SR latch. So now understand a basic memory cell from these latches. Okay, we'll see how the data gets stored. So here I have this configuration. You don't have to worry about like how this circuit came into action. Don't have to worry about that. Just you have to understand the working of this circuit. That's only needed. So let's first understand with reading and writing. So I obviously I will have two extra lines. One will be data in and another will be data out. Data in and data out. that will be present. That is intuitive, but few extra things I have. One is the select line, another one is the read and write line. So what is select line? Select line basically is the line that I need to select, the flip flop that I need to select. So this right is required to select the flip flop, because if I'm doing some write operation and read operation, to where I'm writing and reading, so I have to select that particular flip flop to write or read, right? So that's why this is required. And when this will be 1, that means I have selected this flip flop. If this is 0, that means I have not selected this flip flop. Now read and write, basic thing, right? If I'm reading or writing to the flip flop, so generally this is just a standard. The configuration can be different for different types of flip flop, but in this case for reading, my bit should be high, signal should be high. For writing, this signal should be low. Okay, so first I will understand how to write. So for writing, obviously first of all I have to select the flip flop, so this signal will be 1. Then I have to make this signal 0 as specified. So this will be 0. If this is 0, this will be 1. Okay, this is 1 and this is also 1 due to this, and this is also 1. So ultimately this is my data in that I will give to the flip flop, right? D. Let's assume it to be D. This will be D bar. So this will be D and this will be D bar. Now if this is D and D bar, what do we know? We know, like, this is one of the way which we can make SR flip flop. We can make it differently as well. Okay, the truth table will be different. Just I am discussing about the truth table which has these type of configuration. Okay, so here if I have, this is D, this is D bar, this is D, this is D bar, right? This is S, this is R. If it is toggling, I will always store what? The R value. If it is toggling, I will always, like the Q1 plus 1, this Q1 plus 1 will store the D complement, or like, sorry, not the R value. I will always store the S value. Whatever is the S value, I will store it here, right? In S, what I am giving input? Qn plus 1 will be what? In S, whatever I am giving the input, that it will give me output. So in Qn plus 1, it is D. So Q will give me output as D. So currently Q has D. This is the information stored in Q. Now, what is the output signal of D out? D out is simply 0, right? Why? Because this write bit is 0. So 0 times anything will give me 0. And I am not interested in reading, right? I was just interested in writing. Was I successful? Yes, I was successfully able to write on this SR flip flop my value D. It has stored the value D. I hope you know this. You study in sequential circuits. Okay, this you have taught. This you have learned already. Now let's come to the second case for reading. Reading, how will I read? So for reading, this bit will be 1. If this is high, what will happen? If this is high, this is 0. Now if this becomes 0, this becomes 0, this becomes 0. Obviously the output here becomes 0, 0. So whenever the SR is 0, 0, what is output? Output is memory, whole state, right? Previous, whatever was stored, that I will get as the output. So here I will have Q of the previous N. This select bit would obviously be 1 because I am reading from this particular flip flop. And the read bit is 1, so this is also 1. So 1 times Qn times 1 will be simply Qn. So I will read from here. What will be the output? Output will be whatever was stored previously. So I perform the 2 operations successfully, read and write operations. So this is just a basic building block, okay, of a memory cell. So we have to develop this. To develop this, we need this NAND gates, this select line, all those things, flips, latches we need. So obviously we make this using what? We make this using transistors. Okay, we make this using transistor. So I will show you that circuit diagram. How do we make this using transistor? Remember the basic thing. Basic thing is this latch. This latch is the important thing. Now, what are these? These are, don't worry, I will explain about the working just in a second. Just let's understand the circuit diagram. And always try to remember this circuit diagram. This circuit diagram is very, very important. So this you already know. This you already know. Okay, what is this? This is a pass transistor. Pass transistor. What is the use of a pass transistor? The use of a pass transistor is very, very simple. So basically these are the pass transistor. Transistor is very, very simple. Basically, if this is high, right? If the input of this is high, if this is active, then whatever I have here, it will pass it here, or whatever I have here, it will pass it here. Okay, that's the basic understanding you need to know on the surface level. I'm not going in depth of the pass transistor logic. If this is high, then this pass transistor logic will be active. That means basically if I have a bit 1 here, this bit 1 will be passed here, okay, or vice versa. If I have a bit 1 here, this bit 1 will be passed here, which it depends which side of the transistor is driving. Okay, that is the important part. That is the pass transistor logic. Okay, so what we do is, obviously, how do we implement, this is a NOT gate, right? How do we implement NOT gate? Using MOSFETs. So obviously we don't implement, I've just for explaining purpose I've explained you this circuit. Okay, now I will come to the main circuit. This bit line, right? Bit line is just basically the data line. This bit line is the data line. This select line, I hope you know, is also known as the word line that I have shown here. Okay, just now I am showing you the circuit analysis point of view. Okay, so here I have a static RAM using 4 transistors. So I hope you know how to make a NOT gate using a transistor. All these things, you know, that is my understanding. This is simply the NOT gate. This I have replaced this circuit with what? Using the latch. This was my SR latch, right? I have just simply replaced that. All these things are same. This is bit line, this is word line. These are same, right? This is what? This simply the pass transistor logic. Whatever I have here, it will pass it. Okay. I hope you understood this point. This is how you implement. Okay. Now, how do we pass the value? So here, if this bit line, right, if this, first of all, this word line has to be active. If this word line is active, this pass transistor logics will be active. If these are active, let's say if this bit is 1, okay, then obviously this pass transistor logic will pass this one here, and to the input of the one of the S or R, I will get 1 here, okay, and this 1 will be simply passed and I will get the output. That we already know how to store this configuration. I've already explained. This is simply this SR, right? Already explained this. Just I'm telling you the outside part. Okay. So that's how we store the data. This data will come here. This is cube. This is simply D bar that will come here if this is high. Okay. And that's the working. But we generally don't use it. Okay, we generally don't use it. I will just show you one of the example of memory read and memory write for this NMOS cell. Then I will tell you the better alternatives to these circuits. Okay, there are few better things that we use, because here I have resistors which are very bulky. We don't want to use resistors. MOSFETs are very small in size, so we use MOSFETs. So now let's understand how can we perform a memory write and a memory read on this particular 40 cell. Just this is implementation. Just understand it on the surface level. You don't have to go too much in depth here. So like one more thing, this bit line, right? It is not fixed that this will be bar and this will be not bar. It's nothing fixed. It depends on the implementation, how they're implementing. They can implement it anyhow they like. Okay, so for memory read, I will assume few states. First state is your bit lines should all be high. These lines should all be high, and your select line should also be high. So if this all these are high, then what will happen is that if initially I have some memory stored here, right? This Q data is stored here. So obviously, if this word line is high, then means this pass transistor logic is on. If this is on, this Q will directly be passed on to the bit line, and from here I will have a sensing device that will read this value Q. Whatever the Q can be 0 or 1, whatever it is. Okay. So I have explained you in very simple terms, but this is not that simple. This, right, transition is not that simple. There are many concepts involved, but that is not required. For our purpose, that is not required, so I'm skipping it. Okay, just understand this Q is directly coming here and we're reading from it with some sensing device. That's it. So in this case, my bit line will be high. This will be high, but this, it's okay. This will be pulled high, but this value, right, will be pulled due to this Q register, due to this pass transistor logic. Although this bit line is high, the value will be decided by this Q. Okay, and here as well, this bit by line bar will be high, but ultimately this pass transistor logic will pass this Q bar here, and I will read from here. Okay, and this word line is obviously high to select the pass transistor logic. That is the basic thing. Okay, now for memory write, what we do is we make, like, we assume few states. Initially, let's assume Q is 0 and Q bar is 1. Okay, and my word line is high. Okay, word line is high. Obviously, the pass transistor logic are selected. I have to select the flip flop, right? I selected this flip flop. Now my BL is 1. If I assume my BL to be equals to 1 and my BL bar to be equals to 0. Okay, so what it will do is this value is 1, right? If this value is 1, obviously the pass transistor logic is active. That means this 1 will be here. So this initially it was 0, q bar was initially 0, sorry, q bar was initially 1 only. Okay, q bar was initially 1. Okay, one thing I made a mistake this side. Assume it to be initially 0 and 1. 1 and 0, sorry. Assume initially to be 1 and 0. So q bar was initially 0. Now it got changed to 1. Same here as well. This, right? This is 0. So this 0 will come here, and this pass transistor logic is active. So initially my q was 1. Initially my q was 1. Now it got changed to 0. Okay. So that's how we store the data. Just I have explained you the implementation. It is not that simple. Just I have tried to explain the like basic thing, memory read and write. Okay, that much you need to know. You just need to understand the circuit diagram. You should be familiar with the circuit diagram. So this is the bookish circuit diagram that you should be familiar, because they can ask you the circuit diagram. So this is a 4T RAM cell. Why? Because we are using four MOSFETs, 4 transistors, 4 MOSFETs. That's why it is known as 4T NMOS RAM cell. Okay, SRAM. Now there is another implementation. This is bulky. This is bulky. Why bulky? Because I have resistors here. If I have resistors, resistor will take up very high amount of space. Transistors don't take very high amount of space, but resistors do. So what we do, we change these resistors in place of transistors. We can use transistors as resistor as well, if you know this thing. So these are just resistors. Everything is same. Everything is same. I have just replaced my resistors with MOSFETs. Okay. So the name becomes 6T RAM cell. Why? Because I am using 6 transistors. This is better and less bulky. So more memory density. More memory density. Why you will have more memory density? Because I will be able to store more values here. Okay. Now just one more thing. This, right, all this combination can be made with a CMOS as well. That is what we have done. We just implemented this, right, this whole thing using a CMOS. That is just the difference we have made. So you should know the circuit diagrams. That's the only thing, because this can come with, what is this? This is it again 60 RAM cell, but this is using CMOS. Previous one was using NMOS. Okay, so this is the bookish way of circuit diagram. This much you have to know, nothing else. Nothing else. Now we'll come to dynamic RAM. Okay, on one more thing. The circuit diagram using BJTs. We're implementing the same thing using 4 BJTs. Okay, everything is same. Just the MOSFETs have been replaced to BJTs. The 40 RAM cell, that configuration has been replaced over here. Nothing has changed, right? We don't use this because VJT, first of all, it consumes more power and it is very not efficient as well. So we don't use it currently. Currently, those transistors are only used. Okay. Now, let's come to the dynamic RAM. So what is dynamic RAM? Dynamic RAM stores data in capacitors or in MOS capacitors. Okay, obviously capacitors can be made using MOSFETs as well. So it stores data using capacitors. Capacitors gradually lose charge, requiring periodic refreshing. So in a capacitor, right? In a capacitor, I know there can be some leakage resistance. Okay, some inherent leakage resistance always will be present with the capacitor. So if initially this capacitor was charged to some VDD voltage, okay, what will happen due to this leakage resistance, right? What will happen? It will discharge. Okay. Now, generally, this resistance is very high. Very high. So basically my time constant RC is very high. So it will take a very high amount of time to fully discharge, but still it will discharge, right? Still it will discharge. So from VDD it will go down. From VDD it goes down. So from VDD it goes down, right? From VDD it tries to go down to 0. This is simply a parallel RC circuit, right? But from here only I'm measuring the output of my DRAM cell. Actually, I will show you the circuit diagram. Here I'm measuring the output. So actually it should have shown me 1, but as I have not refreshed the capacitor, that is I have not recharged the capacitor, what will happen? This will totally discharge. Right? Discharge to 0. But actually I should have read back 1, but this is showing me 0, which is wrong. So that's why that is the requirement for periodically refreshing the capacitor so that the capacitor does not lose its charge. If it is high, it should not lose its complete charge. It should keep its charge. So I have to recharge this capacitor. That's why we need periodic. Okay, I hope you understand. So dynamic RAM requires periodic refreshing. That's why the name dynamic, because there is something dynamic, right, about this. I have to refresh it every time. That's why the name dynamic. Okay, operation: place the data on the bit line and charge the capacitor. And read, just access the charge capacitor. That's why, and uses sense amplifier to read back. I will show you the circuit diagram. What is the advantage? Advantage is high memory density, because I only need a single transistor or two transistors. A single transistor will also work with a capacitor. Okay, I'll show you the circuit diagram. That's why it has high memory density, because I don't need many components. But as I don't need memory components, so the power consumption will be low, because only one transistor is required and capacitor is a passive component. But the problem is it is slower than SRAM, because I need to every time refresh it, right? I need to refresh it. It becomes slower than SRAM, and obviously this problem, right? This problem of refreshing is there. That's why we generally don't prefer this. We have to refresh it, and it increases the time as well. So that's why it is slower. But it has high memory density. Okay, because it has less number of components. Okay, why high memory density? Only one transistor and one capacitor can work. Okay, so I will show you the circuit diagram. Very simple, nothing difficult, right? Again, it is a pass transistor logic. This control line is just selecting the device, right? Just like previous case, it is just selecting the device, and I have a data line here. So obviously, if this select line is 1, so this data line will come here, D, and this, right, is a MOSFET. This is using two transistors. One is a pass transistor, another one is simply a MOSFET. This is just simply a capacitor. So this I can equivalently show here. Okay, so if this data is high, so this will be pulled up to VDD. If this data is low, this will be pulled down to 0. That's the only thing, right? So that's how we do simply this pass transistor logic. If you know this basic thing, it charges the capacitor and it discharges the capacitor. That's the only thing, right? If this data is high, it will pull it up to VDD. If this data is low, it will pull down to 0. Okay, how do we read back? We have a sensing amplifier here. We connect a sensing amplifier here. Okay, and we sense the voltage. Okay, if this is low, obviously it will sense 0. If this is high, it will sense 1. This is just a buffer amplifier or sensing amplifier. But I told you, right? Obviously, I have a resistance here that is parallel. This is an inherent property of a capacitor. So it is parallel with the capacitor and it can discharge. So that's why I have to periodically refresh this, periodically charge this, right? How do we charge? That will not come to in this lecture, but just know this concept that we have to periodically charge this. That's the problem with dynamic RAM. Okay, so these are few differentiators of static RAM and dynamic RAM. This can come in your examination. This is the important part. Okay, the working I have explained, the circuit diagram I have explained. The difference that you should know, theoretical points. First is your SRAM is implemented using flip-flops. Your DRAM is implemented using capacitors and MOSFETs. Okay, MOSFETs. Mainly MOSFETs are the device that stores the data, and here flip-flop stores the data. Speed of SRAM will be faster. Speed of it will be slower, because I don't need refreshing here. It will directly store the data, and I will need refreshing here, right? I need to periodically refresh. Now power consumption will be higher, it will be lower. Why? Because I'm using more MOSFETs, like 6 transistors I'm using, right? Here I'm using only one transistor and plus a cap. So it generally takes up very low amount of power. Memory capacity will be low, obviously, because I'm using like 6 transistors. They will take up some space, right, for storing 1 bit of data. Here I'm using only one transistor plus one capacitor to store 1 bit of data, so obviously it will be higher. Okay, now it is used for cache memory, because this has high speed, more speed, because it is faster. Because it is faster, it will be used for cache memory. Because it is slower, it will be used for main memory, that is RAM, read only memory. Sorry, random access memory that is present currently in your CPU. Cache memory is the memory that the CPU directly communicates, right? Don't have to worry about this. This is taught in COA, so don't have to worry about this. Just understand cache memory is the fastest form of memory. So we want to use the fastest form, that is SRAM. And in DRAM, we will use main memory because it is slower. Now, refreshing is not required. Refreshing is not required. Here, refreshing is required. Why I have explained. Okay. So, the power consumption is higher also because we are using BJTs as well. although transistors generally consume less power, but as we are using BJTs, this will consume more and more power. So like, and memory capacity is this, right? In memory will be in the capacity of GBs, 16 GB RAM, 8 GB RAM, your phone has 8 GB RAM, something like that. But cache memory, if you know, it is like kilobytes or megabytes. It is in the form of KB or megabytes, right? Because it is very expensive, but it is very fast, very fast. Okay, so that is just the difference between this SRAM and DRAM. But remember this thing as well, that both are volatile. If power goes off, volatile, everything will go zero, right? Because MOSFET is electrically connected, everything will go away. Everything will go away. Power goes off, both are volatile, both will go away. It is RAM, it is still a RAM, right? Random access memory. And random access memory is always volatile, as explained at the starting of this lecture. Okay, so now we'll come to ROM. ROM is again theoretical points. You don't have to understand anything, just theoretical points you have to understand. What is ROM? ROM is basically data is written during manufacturing and cannot be modified, generally limited in a limited way. It is permanent storage, it is non-volatile, that's why it is called permanent storage. That is, if even if power goes off, still data will be stored. Data will be stored. Will be stored. Okay, so it doesn't matter. It doesn't matter. Now ROM has many types, right? One is permanent and another one is erasable. So although we call it as permanent, but sometimes user may need to program it. That's why it is called erasable and permanent. There are many times. This is simple ROM, which is simple, permanent, nothing can be changed. I will explain the like definition as well. Another one is PROM. PROM is programmable ROM. EPROM is electrically programmable ROM, and EEPROM is electrically erasable programmable ROM. So what are the differences? So first one is mask ROM, simple ROM, that is, it is pre-programmed during fabrication and it cannot be programmed by the user. It cannot be changed by the user. Okay. Next is PROM. PROM is programmable ROM, that is can be programmed only once. Only once. That is important portion here. Only once by the user. User can only program it once. Okay. Be careful here. Now EPROM is erasable PROM. That is, it is, sorry, I told the full form here wrong. This will be erasable and this will be electrically erasable. Sorry about that. So it can be erased. The PROM can be erased using UV light and can be pre-programmed electrically. I cannot simply erase it. I have to like give some UV rays, then only I can erase the data. Erasing is not that simple. Okay, but programming is easy. I can electrically program, just like in a computer you write 1 or 0, you can do it. Okay, but I cannot erase. I have to erase using UV lights. What is electrically erasable PROM? As the name suggests, I can electrically erase and reprogram using electrical signals. Previously, in this type of PROM, I can only electrically program it, but I cannot electrically erase it. So EPROM came to electrically erase it. These are just few types that you should know. This is just theoretical point that you should know. Okay. So now we'll solve few questions. 2017 EC. Okay. In DRAM, periodic refreshing is not required. No, this is not correct, right? Periodic refreshing is actually required. Information is stored in capacitor. Yes, we use capacitors to store the information. Information is stored in latch. No, this is used in SRAM. This is used in SRAM. Both read and write operations can be performed simultaneously. Now, is this possible? No. Can I read and write simultaneously? In SRAM also we cannot do that. Okay, I cannot simply read and write simultaneously. How can you read and write simultaneously? If let's say I'm reading this value and then writing, I'm just reading whatever I'm writing, right? That's not how it works. Okay, so we cannot. Option B will be the correct. So few theoretical questions will come only. That's the most important part that you have to understand. Okay, the minimum number of MOS transistors required to make a dynamic RAM cell will be. So dynamic RAM cell, minimum number of MOSFETs. You can use two MOSFETs. One MOSFET will be MOS cap, another will be simple MOSFET, pass transistor, or you can use one MOSFET, another capacitor. So minimum number of MOSFETs in this case will be 1. We can use minimum number of MOSFETs. This also came in gate. Okay. Now next question: the minimum number of MOS transistors required. Sorry, this right. This should be static RAM. The minimum number of MOSFETs required to make a static RAM cell. Okay, this also came in gate as well. So minimum number of MOSFETs to make a static RAM cell. Obviously, we don't use this. Use capacitors in static RAMs, right? We don't use capacitors, so obviously we use MOSFETs. And the latest generation of MOSFETs that we use is 6 MOS. and that is what we use. We don't use the any other format. We don't use BJTs because those are those are very power hungry, and we don't use the 4T MOSFET and MOS because I have two resistors there, that is bulky. So we use 6 MOSFETs, that is power efficient and less bulky. So minimum number of MOSFETs to make a static RAM cell will be 6. Okay, we don't use capacitors, so option A will be correct answer. So basically this is it about this lecture. Okay, I hope you have enjoyed this lecture. Okay, and this is just a 40-minute topic, not that lengthy topic, and just take it lightly because 1-2 marks question can come, and you see, right, how simple questions can be asked. How simple question can be asked. Few theoretical points you need to know, and you will be simply able to answer the questions. So yeah, that's it from my end from this lecture. I hope you enjoyed this lecture. Do hit the like button and let me know in the comments how you found this helpful as your GATE preparation journey, and all the best for your examinations. Thank you and happy learning.